Welcome back to Thermodynamics, the rules of heat, work, and reality. Today we dive into the bedrock of physics, the first law. It is often stated simply, energy can neither be created nor destroyed, only transformed. But for a physicist, this isn't just a slogan, it is a ledger. Mathematically, we express this as delta U equals Q minus W. This equation tracks the internal energy of a system through heat and work. Delta U represents the change in internal energy, the sum of all microscopic kinetic and potential energies within the system boundaries. Q is the heat added to the system. In our convention, when energy enters via thermal transfer, Q is positive. W is the work done by the system on its surroundings. If the system expands and pushes a piston, work is positive and energy is leaving. Think of it like a bank account. Heat is a deposit and work is a withdrawal. The balance remaining is your change in internal energy. Crucially, internal energy is a state function. It depends only on where the system is now, not how it got there. However, heat and work are path functions. The amount of work done depends entirely on the specific process taken between states. Let us examine a gas in a cylinder. If we add 100 joules of heat and the gas does 40 joules of work, the internal energy increases by 60. In an adiabatic process, the system is perfectly insulated. No heat enters or leaves, so any change in energy is purely due to work. In an isothermal process, the temperature remains constant. For an ideal gas, this means the internal energy doesn't change at all. An isochoric process happens at constant volume. Since the system cannot expand, it does zero work, and all heat added goes directly into internal energy. If we zoom out to an isolated system, like the entire universe, the first law tells us that the total energy is constant. It just shifts forms. This law forbids perpetual motion machines of the first kind, devices that claim to do work without any energy input. They are physically impossible. We owe much of this understanding to James Prescott Joule, who proved that mechanical work and heat are just different manifestations of the same thing. He established the mechanical equivalent of heat, showing exactly how much work is required to raise the temperature of water. So why is this useful? Because it allows engineers to calculate exactly how much fuel is needed to generate a specific amount of power. The first law applies even to your own body. The chemical energy in the food you eat is converted into the work of your muscles and the heat of your breath. While energy is always conserved, the first law doesn't tell us if a process will actually happen. It only says the energy accounts must balance. For the direction of time and the quality of energy, we need the second law. And that is where things get truly interesting. The first law is the ultimate reality check. Energy is finite, it is measurable, and it is never free. We will see you in the next episode. Thank you for watching Spacetime Softmax. Don't forget to subscribe for more deep dives into the laws of our universe.